Okay. So yeah, as I said, I'm a scientific software developer and a quant researcher. Formerly, I was quant at Bloomberg and adjunct faculty at Columbia and NYU. And I founded QuantStack in 2016 when I returned to France last year. So I'm also a Jupyter core developer, and I'm especially invested into the Jupyter interactive widgets and other packages built upon Jupyter, which are BQplot, PyQGIS, and IPyLeaflet. But what I'm going to show today is not just my work. There are 3 other people that worked really hard to make this possible. So first, I'm just going to mention Johan Nabil, who is also at QuantStack. He co-founded the company with me last year, and he co-authored most of the packages that are going to be presented. And Wolf Volprecht, who started contributing about a year ago, just by himself, and joined QuantStack in last October. And finally, I also wanted to thank Loïc Gouarin, who is a research engineer at the Laboratoire de Mathématiques at Orsay. And he co-authored Xeus Kling, so actually the bindings between Xeus and Kling, which I'm going to demo today, and Xplot, which is a plotting library that was built upon this entire stack. I'm guessing that most of you are already familiar with what Jupyter is, but basically, Jupyter is a software stack that is meant to improve the workflow of researchers and educators who are using code in their, not just to build systems, but to explore problems or to present them to a larger audience. And this is something that is really key here, is that most of the software engineers actually make use of programming languages to build large systems that are already specified. But what we do as scientists is very often different from that. It's that we are trying to use the software for exploratory analysis. We run some code, we look at the visualization, we do some data, run more code. And this quick iteration is especially important during the exploratory phase of a project. And this is really what the fact that it was already possible with a number of interpreted programming languages like Python and Julia and R made these frameworks really, really popular. And actually, the Jupyter protocol and file formats brings together all of these languages around a common standard for communication with an interpreter, and visualization, file formats for communicating the results. Most of the kernel the kernel is a part of the Jupyter infrastructure that is responsible for executing the code that the user writes. And most of the kernel have their own implementation of the protocol. So Python, the IPy kernel reference implementation implements fully the kernel protocol of Jupyter. We have another implementation in R and Julia, but many others actually make use of what I would call the wrapper kernel approach, in that they use the implementation of IPy kernel and inherit from the base, I would say, kernel, and either capture the output, textual output of their interpreter, or try to do something more sophisticated, but don't really make use of a native implementation in the target language. So this is an issue because actually implementing a protocol like that of Jupyter is a very big overhead if you want to expose your language to the Jupyter stack. That's why it's really important that there is more synergy between this programming language and that we agree on a common implementation that would be in the language that is the common denominator between Python, R, and Julia. So another issue with the wrapper kernel approach is that there is a dependency on the Python runtime, and you may not want that. For example, we may just want to have a simple executable that speaks the protocol but doesn't require Python, IPy kernel, and all the dependencies. In fact, a kernel, it's merely an executable that implements an inter-process communication protocol. It should be really lightweight. So today, I'm glad to announce Xeus, which is a modern C++ implementation of the Jupyter protocol. And it's not a kernel itself. It is meant for enabling kernel authors to create new kernels without having to deal with the protocol. So it makes the task of creating a new kernel for a new language really easy. So a quick example, for example, if you want to create a simple echo kernel using Xeus, all you need to do is inherit from the base Xinterpreter class that is exposed, which is a virtual class, and implement a few private virtual methods. So execute request imp, complete request imp, inspect request, history request, etc., etc. And these functions take really simple argument types and a very short glance at the protocol documentation, and makes it really simple. It makes it really simple to understand what you need to implement in there. If you want to bind your own language, when this language has a C API like cling, all you need to do is include the right headers at the top of this file here, and in the implementation of these virtual methods, make use of the C interpreter API. So what can you do with Xeus? And the first showcase kernel that we decided to make for Xeus was actually a kernel for the C++ programming language based on cling. So cling, I guess that you all know what it is. I usually make a quick introduction to what cling is and where it comes from, but you probably all know much more than me on this subject, so I'm going to pass. And I'll start with a demo. Okay, so I need to restart the notebook. There we are. So here I just launched a Jupyter notebook, and the first thing that you can probably see in the corner of the screen is that the kernel that is launched is the Xeus C++14 kernel, right? And I'm going to make use of the simple uses of the C++ programming language using the cling interpreter. So if I just print some output using CAD, the outputs are redirected to the front end. Same thing for the errors of that may be printed to the standard error output, and they will be displayed with the right styling. We also catch exceptions and display the messages in the UI. If you omit the semicolon in the last statement of a cell, the type of the last statement is going to be printed, just like in cling. And if you don't, it's not. So I usually start with a demo that actually cling supports, has a really good support for the programming, the C++ programming language. So classes, polymorphism, templates, C++ 11 and 14 support. One feature that is especially interesting, I guess that you would be interested in as cling users, is that we enabled some parts of the Jupyter kernel protocol that are usually not implemented for languages that don't have a native kernel for a long time. So for example, if you do !std vector, what you're going to see is a live help from CPP reference for std vector. And the same holds for anything in the standard library or other libraries that we have enabled, where the help is going to be fetched on read the docs. There are also a lot of other goodies in the Jupyter protocol. We can also use the rich display data mechanism of Jupyter. So here, for example, if you want to display an image in line in the notebook, it's fairly easy. We're going to provide a higher level API to do this than the one that I'm displaying right now, but this is already showing that it's possible. Or we can also display other MIME types like sound. And in this example, I'm just playing a sound in the notebook. I don't know if you could hear the music, but for me it was really loud. So yeah, this is basically the first demo notebook that displays the use of the cling kernel in Jupyter. Where are my slides? Yes, yeah. Other pieces of the stack that really made the Python scientific stack, among others, are really powerful is the flexibility of the different libraries that were available and widely adopted within the community. So one is NumPy, another one is Pandas, and also the plotting library. So I just wanted to mention another work that we've been working on in the past year and a half, which is Xtensor. And if for those of you who may not have heard of Xtensor before, a very quick way to summarize what it is NumPy, but in C++. So it's a C++ template library for multidimensional array manipulation. It follows the idioms of the C++ standard library. So we have iterator pairs, we have the value semantics, very clear value semantics, but also an API similar to that of NumPy. So, and there are many other things that come with it. So we have Python bindings to enable the Xtensor API on NumPy arrays. We have Julia bindings to enable Xtensor APIs and Julia arrays, same in R, and we also have Jupyter projects for authoring Python, Julia, and R extensions using Xtensor and these bindings. What else? We also have BLAS bindings that enable operations, BLAS of Xtensor expressions. And we have bindings for the ROS, robot operating system, and for ImageIO for reading, writing images, and sound files. And finally, we also have bindings for FFTW. It's not over. We also have SMD acceleration kernels that are plugged into the system to make Xtensor fast. And it's all open sourced and BSD licensed. So to make a quick comparison between Xtensor and NumPy, in this example, I'm showing some Python 3 NumPy code and on the left-hand side of the slide, and on the right-hand side, the equivalent C++ 14 Xtensor calls. So NumPy arrays NumPy has one type of container, which is the NumPy array, and the C++ 14 Xtensor library offers two types of containers: the Xarray, which is basically the same thing as the NumPy array, and the Xtensor, which has a static dimensionality and is a bit faster for certain things, but can also be reshaped as soon as you don't change the dimension. And we have constructors, builders for tensors like linspace, logspace, arange, I, zeros, ones. We support views, broadcasting, vectorization, fancy indexing with filter index views. We have mathematical functions for sum, so reducers, sums, products, mean. We support Boolean operations. All the standard functions from the standard library CMath. We have a random module that is very similar to that of NumPy, and things like concatenation, etc. And much, much more. So fancy indexing, broadcasting and universal functions, linear algebra, language bindings, lazy computing, views and array and expression. Yeah, because indeed, actually, one big difference between Xtensor and NumPy is that everything is actually lazy evaluated. In NumPy, linspace returns an array, while in Xtensor, what linspace returns is an expression that can be used just like an array, iterated upon or accessed with the square bracket operator. But it is not an array. There is nothing that is allocated when you write auto x is equal to linspace. The same holds for mathematical operations and other. We make use of a technique called template expressions, which is a really known and popular technique to achieve these sort of things, to have a lazy evaluation in Xtensor. I'm going to pass this very quickly because I don't have so much time. So just like NumPy and libdyne, we support broadcasting. So operations and universal functions are actually parallelized and vectorized. And broadcasting is actually recursive. We offer a number of iterator pairs. So begin end actually is a simple row machine. Or we can provide a broadcasting iterator where if you provide a shape, it's going to give you an iterator pair that is going to iterate on a vector or a tensor just as if it had a different shape. We also offer different means of iterating on a tensor using column major or row major layouts. And this is true for any tensor expression, not just those that are evaluated. In Xtensor, things are only evaluated upon access or when you assign it to a new expression, to a container. We support views that are L values, so when you try to modify, you can modify two values of a view and it will modify the underlying array, etc., etc. All that you can expect from a complete ND array library. We also have a meeting value support using a technique called reference proxies that is a bit different from how the STD optional works, but is really much more flexible because it allows us to express optionality in a very diverse way and to deal with things such as optional assemblies where the optionality or the presence of an expression or a value is given in a different array or tensor. I'm going to give you a quick demo of Xtensor and Xeus working together. So Xtensor, here I'm just including IOStream, XArray and XIO, defining two arrays and adding a row of one of the two arrays and to the other array that is one-dimensional, and you get what you expect. We can also initialize a 1D array and reshape it in place and display it. Or using universal functions with broadcasting to compute the power of one array with respect to another. The random modules is also very similar to that of NumPy. Also can display the builders, A range, ones, zeros, mesh grid, broadcasting. And you can also use the STL algorithms with expressions. So here, for example, I'm accumulating all the signs of, no, I'm accumulating all the values of a random expression that is actually not even evaluated before I access it. There is no allocation whatsoever. Or iterating over a prescribed shape. Xtensor BLAS is the library that offers the BLAS bindings for Xtensor and can be used for doing all the NumPy lineage operation. So if you are interested in knowing more about Xtensor and have the time, you can consult the documentation that is on xtensor.readerdocs.io, and here we have a fairly comprehensive NumPy to Xtensor cheat sheet where everything is actually documented from containers, initializers, broadcasting, random, concatenation, diagonal, triangular and flip, iteration, logical operations, comparisons, complex numbers, reducers, I/O, mathematical functions, linear algebra. So that is for Xtensor. And so as you've seen, actually Xtensor plus the C++ notebook together offer an experience to the user that is very similar to that of a Python user using NumPy in the notebook. So another area where Jupyter really shines is for doing interactive computing with widgets and visualization. In fact, even with an interpreted language, if every time you need to change a parameter for a computation, you have to modify the code and re-execute the code, it is still really cumbersome. And there are much more powerful way to modify many parameters at the same time by by being able to use the mouse in 2D or 3D visualization. As I'm here, I'm just going to display some of the important plotting and visualization libraries that have been built upon Jupyter. So one is IPyLeaflet. IPyLeaflet is a set of bindings between the Jupyter widgets protocol and the Leaflet.js mapping library in JavaScript. And it enables the visualization of maps in the notebook, or on which you can even draw or retrieve coordinates from your mouse on the Python side. BQplot is a set of bindings between another JavaScript library called d3.js and and the Jupyter widget protocol, which is then enabled in Python thanks to the IPy widgets implementation. Here we have a very simple scatter plot in 2D thanks to a big plot visualization. Py3.js is another one that I've been working on for the past few years, and it's a scene description library in JavaScript that is essentially a wrapper for the 3JS WebGL 3D plotting library and the Jupyter widgets protocol, and also Python bindings in the backend. IPy Volume is a fairly newcomer. It's a really fast plotting library in 3D that, just like Py3.js, is also built using 3JS, but offers higher level routines for doing scatter plots, visualization of density plots in 3D using transparency. You can do animation, and since it's a widget library, just like BQplot and Py3.js, it can work really easily together with these libraries. So if you go to the jupyter.org/widgets website, you're going to find a gallery of it, and if you find IPy Volume there, click on the play button, you will see a really smooth animation of the movements of stars in the galaxy. This is a small one that can be contained in the web browser, but this library has been used for really large-scale data visualization in the context of visualizing the Gaia dataset, which is one of the largest astronomical datasets. And it's actually written by an astrophysicist. NGLView is a protein visualization library, etc. So as you see, the widget library, the widgets protocol is really one of the strong points of Jupyter in terms of interactive computing. And so the way this works actually is that when you use IPy widgets, so the Python implementation of the widgets library, we have a Python objects, which are the widget objects that are automatically synchronized using an observer pattern with a front-end counterpart, which is a widget model. And every time we display a widget inline in the notebook, a new view object is created. A new view is created in the front end, and you have the visual representation of your widget. Then when you change the data for let's say a slider widget, automatically the front-end model is going to be updated, and the views are going to reflect that new state. In fact, the communication protocol between the kernel and the model and the front-end model object is very well specified. And since most of the logic for the rendering of the widgets is implemented in the front end, we have a situation where the backend is really thin, and it's not hard at all to create a backend for another kernel, for another language, for all these widgets libraries. So this is what we've done. Before I get to this, we have, so here is a quick example for the slider widget. And all there is for the implementation of the slider widget in Python is the declaration of the class and a few of the data attributes that are synchronized with the front end. So here we have the step, the orientation, the readout format, whether we handle continuous updates on every mouse move, or if it's only when the button is released, and a disabled attribute. And that's it. And all you need to do is replicate this in the C++ and implement the magics of the observer pattern in the base classes. So basically, the foundations of the C++ backend for Jupyter Interactive Widgets, it's an implementation of the observer pattern that we use. So the one in Python is called threadlets, and we have another library called xproperty, and the implementation of the Jupyter Widgets communication protocol, xWidgets. So let me give you a quick demo of the xWidgets library. So right now, the xWidgets library, as it is a bit slow because there is a lot of compilation of templates going on, but we have found a solution to that problem like recently, and we have been experimenting with doing this at scale for other widget types. So here I have just instantiated a widget and called a slider, and called slider the display. If I change the value for the slider, just writing slider value is equal to 20, I see the value reflected in the front end. On the other side, if I move the slider value with my mouse and I ask for the value in the C++ side, I see the right value displayed. I can change other attributes, such as the max, the handle color, the slider orientation, the slider description, etc. And we have implemented backends for all of the widgets that are available in the core Jupyter widgets library. So we have progress bars, numerical outputs, timers, Boolean widgets, toggle buttons, string widgets, so labels, HTML widgets, text area, password. For example, here we have a button widget, so a simple one. So you create a button. Again, we have this compilation time issue. Then I wire a callback to the click event in C++. And whenever I click on the button, I see click being displayed in the notebook. I can also change other attributes of the button. Another widget I wanted to show you just for fun. So just to show you that you can very easily modify attributes of multiple attributes at the same time. For example, in a situation where you want to modify the position of a camera in the 3D environment for 3D visualization, sliders are not quite the best thing because you can only modify one parameter at the time. And all of you that have been playing with video games know really well that there are better means to modify the position of a camera in a 3D environment. And actually, the browser implements support for controllers and game controllers. So here I am simply instantiating a controller widget. Again, there is this compilation time issue with widgets that is going to go away in the next release. Now, if I display that widget, I'm asked to connect a gamepad controller. So I actually own a Xbox 360 controller that I actually bought just for this purpose. I don't play video games. And once it is plugged, I see the state of the different buttons and axes of the gamepad displayed inline in the notebook. So as I move the sliders or the different buttons or triggers, I see the values reflected in the front end. And I can wire events or callbacks to this quantity really easily. Yeah, so that's it for X widgets. How much time do I have left?
10 minutes. Yeah.
Okay. So another thing that I wanted to show you before I move on to the questions is, so this demo only covered the core widget library and the backends for the widgets that are in the core widget library. But as I said, it's actually a framework upon which you can build, and there were many other libraries like IPA Volume, Python.js, BQplot that were built upon it. And we have already started implementing backends in C++ for these plotting libraries. So one that is especially dear to me is the BQplot library, which I co-authored when I was quant at Bloomberg. And the BQplot library is a 2D plotting library for the Jupyter Notebook, but which also works outside of the Jupyter Notebook. That implements the constructs of the grammar of graphics. In terms of API, it's very similar to ggplot in R, but it's all based on Jupyter widgets and was implemented from scratch using Diff3.js. So here I'm just displaying a pie chart inline. So I have this compilation time issue again, and there you go. You have a 2D pie chart. Now I am setting the animation duration for the figure, and as I change the values in my C++ code for the different parts of the pie chart, I see the changes reflected in the front end. So exploit was an example that was especially dear to me because we've worked really hard on this one. And so we support all kinds of other visualization types. Here I'm just going to show a scatter plot updating as I change the values in C++. Sorry, lots of widgets to instantiate. And so the trick is that there are many templates to instantiate, but we already know these types before, and so we're going to provide a runtime, a compile runtime for these libraries so that Kling doesn't have to compile them on the fly.
Yeah, also one note, you probably want to listen to Raphael's talk as well. So this is also going to fix the template instantiations.
Oh, okay. If you have a pointer to this, I would be interested.
Right next to your talk.
Oh. So, okay, this is the danger of live demos. It's not working. This should work. Sorry, I don't know what's going on here. I just played with it 5 minutes ago. Well, exploit is still at a fairly early stage, but we are making quick progress. And Loïc Gouarin, who is one of the 4 people that I have mentioned in the beginning, is really pushing this a lot. Yeah, and now as I change the values, I don't know why it didn't work the first time. It's the first time I said this, but yeah, I see the plot update. I guess that with the latency, you don't really see this, but all of the animations and all of the different, I would say, things that happened were really smooth, and so yeah, it's actually fairly fluid for a user. So some credits. So just wanted to mention again Johan, Loïc, and Wolf. And in terms of resource, many links. So the GitHub repositories for Xeus, Xeus Kling, Xproperty, Xtensor, Xtensor Blast, Xtensor Python, R and Julia, XSIMD, FFTW, IO, ROS are all on Quantstack, except for Ross. Ross is in the Wolf organization. He has been doing this outside of work. And Xtensor FFTW was authored by Patrick Boss, whom I think is involved in Root somehow, and it's under his GitHub account. And Xwidgets and Exploit are also under the Quantstack organization. And we have extensive read the docs documentation for Xeus, Xproperty, all the Xtensor libraries, and XSIMD. That's it. So I'll take questions if I still have time.
Yeah, absolutely.
Yeah. Thank you very much, Sylvain. And yeah, it was very interesting to see even the cases that even big companies are not doing online demos, right? I mean,
yeah.
Like, and it just worked flawlessly. For me, it was really impressive. So, questions?
So this is Mike Sokolov. So I'm part of Diana, and so I have 2 questions in there, somewhat related, maybe not obviously. The first is, if all code is open source, how do you make money? And then the other question related to that is, would you like collaboration from people working on LHC experiments? Would you welcome that?
Okay. So the answer to the second question is yes, very much.
Okay, I will contact you about Diana fellowships.
That would be fantastic. I would be thrilled. But I'm going to answer the first question. It's a bit longer, so that's why I started with the second one. In terms of how we make money, the way we've been making money is with a consulting model economically. Most of this is actually sponsored development. And 90% of this work has been, I would say, sponsored by Bloomberg, that is my former employer and very, very involved with the Jupyter stack. They are the main sponsor and the main developers behind the Jupyter Lab initiative, for example, if you're aware of it. So yeah, it's sponsored development. We are actually also using this stack for the development of proprietary code, but I would not say, I mean, it's not a freemium model. The proprietary code in question would not be of interest, I think, for a larger community. It's very specific to the use case of our clients.
Okay.
Great. So I will contact you separately. Thank you.
Thank you.
So as you probably know, here at CERN and for physicists that collaborate with CERN experiments, we already have a C++ kernel, right, for Jupyter notebooks, which is also based on Cling, but it's what you said. It's a wrapper kernel. It's built with on top of IPython, the IPython kernel. So the question would be, what you know? Would you be able to make a comparison with what's to gain in switching to C++ kernel or to your implementation? What's to be gained in with one thing with respect to the other? Would you suggest that the physicists switch to the new thing? You know, can you discuss? You know, can you compare and discuss?
Yes. So there is one small thing that was really important for other kernels that we're building using Xeus. We are, for example, working on an SQL kernel, and people didn't want an SQL kernel to depend on the Python stack. So for a wrapper kernel approach, you actually need Python, right? Which is a bit heavyweight, given what the kernel needs to do in addition to the interpreter. Another enormous advantage of using such an implementation is that you are actually using your interpreter as a library and embedding it in process, and you have the possibility to expose objects from the compiled wrapping code to the interpreted code. And this is how we actually expose the interpreter instance itself. That is, I mean, the X interpreter, which is an object in the Xeus implementation, and how you can explicitly send messages to the front end from your interpreted C++ code. That is absolutely necessary for implementing widgets, for example. And for the rich display mechanism, so being able to inspect the Clang AST of the things that you are getting back might be a very powerful way of providing information to Jupyter's rich display system. Does this answer your question?
Yeah, I was already in contact with you on Gitter. I was the one that was discussing adding magic, like third-party magics to.
All right.
Kernel.
Sorry,
yeah.
you're very blurred on the picture, so I did not recognize you.
Yeah. So this, it's kind of answered. There are other things, right, that you, on the other hand, are harder maybe to do because, like magics. Okay.
I don't think so.
So,
I think
I'm
it's
trying
very.
to get a full picture.
Yeah, I think it's fairly easy to make magics. Writing an extension or plugin mechanism like you were just suggesting would be as hard in terms of architecture in Python as in C++, in my opinion.
Okay.
Thanks.
More questions? If not, I have a little, I don't know, suggestion. Can you contact also Oksana and then put those materials next to the agenda so that we have it for bookkeeping quizzes and people that are going to look for those? Ideally, I saw you're using the JavaScript thing. I never learned how to export the PDF, but if you can export the PDF, the presentation would be great. So
Yeah, it will be cool.
have it for.
Okay, I will do that.
And again, I would like to thank you for the nice presentation, and you got a lot of clients, I guess, after it. So let's move on to Raphael.
Yeah, right.
I don't think this works.
Yeah. Yeah.
Test. No. Okay, it works.
Okay. Wait, full F11. Okay.
Is it dark? Or
I think we need to turn up the light. I will turn it. So yeah, we will now we will look about presentation of Raphael, that he was working on C++ models in root.
Again, it's very hard to hear you.
Can we get this one?
Yes,
I might be the only one, I'm not sure.
I will shout. No
That's
worries.
much better.
So yeah, we will listen now the report of Raphael on his work on C++ runtime models for root and particularly for CMS software stack. So let's see.
Yeah, test. Okay, so this works. Yeah, hi, my name is Raphael. I work for CMS, and I'm working on the C++ runtime modules in root and also in Clay. Yeah. So, what are C++ modules? So, when we're talking about C++ modules, I mean...
You're also fairly faint.
Ah.
He's a bit ill, so...
Yeah, I'm a bit ill, so maybe I'm not the loudest.
Because of the angle it's
Is there some way to make an adjustment on the microphones in that room?
Wait, let's do this way.
Sorry, could you also share the slides, please, if you're...
They're not shared. Oh my
Great.
god.
blue button.
Blue button.
Yeah, that's what they usually say.
And now, better?
We have to maybe look at the television.
Yes, thank you.
Sorry.
Then the
X11. Okay.
Works?
Yeah.
Okay. Yeah. So this is about C++ modules in root and C++ with the end goal to have CMS SW running with C++ modules. So when I'm talking about C++ modules, I mean Clang C++ modules. There are currently two proposals how C++ modules is implemented, and Clang has multiple module systems. But the system we're talking about is the C++ modules implementation in Clang that works with current C++. A C++ module is nothing more than a precompiled header. So we parse C++ code and we save it in another format that we call a precompiled header. And then Clang loads on-demand code from this file if it needs one. So for example, you take the header vector, the compile vector, the class vector, and all the functions, and then we save it in a file. And when we actually need vector, or Clang sees it needs the declaration or the code that it needs to understand what std vector is, it goes to the file and only loads this class and the functions that it needs into its parser to understand what std vector is doing. So modules are developed by Google and Apple mostly, beside us, and they implemented, yeah, they're mostly developed by Google and Apple. They implement this in Clang because they're both using this in the end to compile their backends. The goal of Google and Apple is that they actually want better compilation times. So C++ doesn't have the best compilation times, mostly because we more repeatedly reparse headers. So for example, you have a header and you include it in 10 files, you need to parse it 10 times to compile 10 files. So the idea from Google and Apple is that they actually use modules to bring down the compilation times. By reducing the parsing time, they actually spend reparsing the same header over and over again. Yeah, so the code they have is open source. It's in Clang, it's upstream. Also, the Google and Apple guys are actually working with us, so we have a wire there, and you can give feedback and can request stuff. Yeah, I said so they work very similar to something that we call precompiled headers. Some of you already know PCH, which is precompiled header, which is more or less implemented in the same way as modules. They share the same code base in Clang. The main difference is that you only have one PCH attached to Clang. So you can say Clang, attach a PCH, but you can only do this once. So you can't actually attach multiple PCH to a single Clang instance. So you can't have one PCH for vector and one for map and then attach both. You can only have one that includes both vector and map, for example. So this isn't very flexible. So the idea is, why don't we just include multiple PCH to a single Clang instance and get the performance benefits and actually not parsing code, but just loading it from these precompiled headers. And this is more or less what C++ modules are doing. It's nothing more than a system which has a lot of changes on top of the PCH that in the end allows us to attach multiple PCHs to one Clang instance and still have a working Clang parser that under the hood just gets all this code instead of from headers from the precompiled headers. So the idea of Apple and Google is that they get their compilation times down. What we want to use modules for is that we say, okay, if precompiled headers are faster than parsing, and we parse headers during runtime in root or in cling, then also runtime gets faster if we actually are able to use C++ modules during runtime instead of parsing headers during runtime to get our code. So a good thing about the C++ modules in Clang is that we actually don't need to do a lot for this. The modules in Clang, of at least one of the systems in Clang, C++ module systems in Clang, don't require any code changes to C++. It works with current C++ 11, 14, 17, I think even with 0.3. So you don't need to add any C++ specific code. It works with Clang and with modules, but the same code actually also works with GCC, for example. The only limitations we have is that we have a few new requirements for the headers that land in the precompiled headers or in our C++ modules. The new requirements are mostly every header needs to be standalone. So if Clang parses header, it needs to understand what's in the header. So if you say std vector, you need to include vector. Otherwise, Clang doesn't actually know what std vector is for. Same goes, for example, if you have in a vector, you say you define a function, and the function has like as an identifier macroname, and the macroname is supposed to come from like a person that includes the header. This no longer works because we pre-compile it once. So we only see what we would see if we just look at a header. We don't look at things that people are including this header or stuff like this. So it's a file. It needs to be standalone, and all Clang sees is this standalone file. The other thing, which is not that big, is no cyclic dependencies between C++ modules. Usually people don't have this already because they also link things together. So if you have a group of headers and you form them into like a C++ module, you say those headers go together in a single module and they get compiled together. Then those headers can only include other groups of headers that are, in reverse, not including ourselves. So we can't have a cycle in a dependency graph. And that's pretty much it. You don't need to do any more.
And it's also good. This is good for finding glaring violations, right? So
yeah.
Good on the both sides.
Yeah. So actually, one of the advantages is that Clang shares a pretty good view of how all the program looks. So it no longer just sees your CPP file and the header files you include. It actually sees more or less everything that you throw at it, and it actually can handle that you, for example, have all the header files in your system. It more or less looks at them and then can say you define the same function, the same namespace in two different header files and gives you a warning. But previously it didn't really work that well because you would really need to include everything. But in Clang, it's in theory possible that you have like very good code checks based on this module system. Yeah, okay. So we want to use modules in root and CMS. So we have a work plan for how we get from our current state, which is that we don't use C++ modules, to the final state, which is that we actually use C++ modules in CMS during the runtime. So our work plan has 5 steps. We compile root to C++ modules. I go to these steps in depth later, but just for overview. So we compile root to C++ module. So we just use Clang to compile it. Then we actually tell root cling to generate C++ modules that we need for root. Then we attach the generate C++ modules to root's runtime. And then we do more or less the same for CMS. We compile CMS with C++ modules. And then we start activating the root module support in CMS and get CMS running with C++ modules during runtime. So the first step is compiling root with C++ modules. So in the current master, what you can do is you can get root, you can set CSX modules on. You need a recent claim, and then root compiles with C++ modules. So the compilation of all the CSX files in root is actually done with Clang, with modules activated, and there's more or less not a lot of header parsing involved. It just actually compiles the C++ modules for root and then loads the code it needs from those C++ modules to compile all the CSX files. The main point for this is why we're doing this is because we want to, first of all, catch if you have regressions in Clang. So we just can recompile the night to Clang and see if root still compiles. And if it doesn't, then we can say, okay, someone broke some part of our root code in Clang upstream, and we can actually make good bug reports. Yeah, and this is more or less done. This is already done, like I think, more or less when I started. So the second step is, now that root is compiling, we actually want to tell root cling, which is responsible for generating dictionaries, that we actually want to start generating C++ modules that we can use in the root runtime, so that cling actually can use during runtime when parsing, instead of parsing code. So the way we did this is we said we have an environment variable that is more or less the start setting we had. If you set this to 1, then root cling is supposed to produce also a C++ module on the side. You run root cling, but you get, instead of the usual files like root map files and dictionary sources, you also get a C++ module on the side. So this is more or less the only change that happened to root cling. It needs the usual module restrictions on all the headers. The headers need to be standalone and so on. But otherwise, not a lot has changed to root cling. The only change that happened is that root cling now needs to respect the dependencies. So if root cling, for example, uses another dictionary that is supposed to land in a module, then root cling actually needs to run behind the dictionary generation for this module. The reason for this is that when we generate a module, for example, for dictionary A, which uses a dictionary B, like headers from dictionary B, then we actually need to make the link say that this module depends on this other module. So we need to generate the other module first, but then when we use A, we just use the other module instead of parsing the headers from there, and then we actually save down the link and say if you load A, there's a module B which gives you the remaining information you need. Yeah, so this works. This is also status completed. Yeah, so the third step is we want to use C++ modules during root's runtime. So we actually want, if we start up root, we don't want to parse headers anymore. We actually want to say, if you, for example, include, or if you load a dictionary, don't parse the headers that are in the dictionary or needed for the dictionary. Just attach the C++ module and load from there if you need any code for this module. The way we implemented this is more or less that we kept many parts of the old system, but in parallel we also have the module system running. So it's in theory and practice also possible to mix C++ module dictionary and non-C++ module dictionaries. So if you have a dictionary and you want to run it with C++ modules, you more or less generate it like in the slide shown before with root modules equals 1. You get a C++ module, and then during runtime, if root loads this module, it actually, instead of parsing the headers, it just attaches the module. Same goes if, depending or not the module has a C++ module. If it doesn't, then it just parses the headers like before. Yeah, so one of the original plans was that we actually completely remove many parts of root and replace them with C++ modules. One of the parts was the root map files, which is a mapping, for example, that says, if you have this class, load this module or this dictionary. We didn't do this, at least for now, mostly because the performance of root map files is better. Mostly because the root map files have like a very simple view of how things work, and they're very slimmed down. They don't work all the times, but they're much faster. So we kind of settle up on root maps and say, people are used to root maps and they want the performance from root maps, but we improve on the performance by actually replacing the backend, which is parsing headers, with actually attaching C++ modules. Yeah, so the status of this is more or less completed. We have 40 tests failing in the root in the root master. We mostly know why most of the tests are failing. It's just figuring out what's the right way to actually fix those remaining 40 tests.
Are those the VC ones? Are those the VC ones?
Yeah, VC is, for example, one, and there's some other things. Yeah, so actually, let's look at the performance you get from using C++ modules during runtime. So what you're actually looking now is time. So this is actually wall time. So usually what we get is like a 25% speed up on startup on normal tutorials. So you have a tutorial file, you run it with root with modules enabled, and usually get a 25% speed up.
What do you mean startup?
It's the time that you get from, like you have a tutorial that more or less does a lot of code, but it's before you actually start executing like actually workload, like writing from files or reading from files. It's like getting all the code that Kling knows what to do.
Root interpreter startup
Yeah.
time.
Yeah. So the time if you type root.exe on a macro, and then the time between you type this and the time between it actually starts doing real work and it's done parsing everything it needs, like all the classes, all the headers, and all the modules it needs to do its workload. It obviously, if you do a lot of workload, then this percentage is obviously just a small part of your runtime. So it's not like everything is 25% faster. It's literally the time that we actually usually spend on header parsing, this kind of stuff. So this is 25% speed up on this. We have around 35% if you use things like, for example, Boost. So Boost has a lot of templates. Boost has a lot of code in there. So if you actually want to parse this during runtime, you spend a lot of time, things like actually parsing code, things like lookup and template resolving. And this is already done in the module. So we're only loading the declaration from the module. We still instantiate templates if you instantiate one that are not in the module. But more or less the time saving is that we get rid of all the parsing time we previously spent on those libraries. This excludes things which are currently in the root PCH, because the root PCH is more or less just a module. So it's one module against multiple modules. It's the same code on the end. So if you have root PCH modules, it's more or less the same runtime. Yeah, but in general, the idea is that you always have better runtime because we always get rid of the parsing time. So this is going to, in general, one of the things that we're we're aiming for, and we probably are going to get, and we already have. So the other thing is runtime memory. So one of the problems we have with memory is that modules use mmap, so they memory map the module files from the disk into our memory. This makes it a bit hard to measure the memory. So if you map 300 megabytes file and the kernel actually sees it already has this available somewhere in some pages, and we just say, we just want to read it, then you actually get a lot of RSS memory because it just says you have a 300 megabyte file, it's a module file, and you get it to your RSS because it's already loaded. It doesn't actually mean that we actually use 300 megabytes. So what the reason why we memory map is because we jump in from Clang on certain offsets and get certain pieces of code that we stored at locations. So this is why we memory map. We don't actually need the whole file in memory, but Linux is actually doing it for us, or the kernel is actually doing it for us. Yeah, so in general, this is the RSS memory, so we're not going to measure this because it goes up and down depending on what the kernel actually thinks it needs to preload or not. So what I'm looking at is allocated memory. So in general, if you look at different tutorials and different use cases, it more or less goes up and down, but plus minus 20%. The memory usage really depends if it goes up or down, but this amount is more or less how the code looks like. If you have code that is more or less normal C++ code that's not optimized for passing fast, so you don't have forward declarations everywhere and try not to include things. In this case, we have good improvements because things like includes are really, really cheap with modules. Or for example, you include something and you don't use anything from it, then it's more or less free. If you use something and you use just a few things from it, then it's also very free. But if you actually use something and you literally use everything from this header, then we don't see a lot of improvements because the people already optimize the stuff we're trying to optimize, which is not loading things we don't need. So if you have already code that is already just using forward declarations everywhere possible and is not including anything you don't need like 100%, then you won't see any improvements. And you still get the overhead from the modules lookup, so this is why it actually goes also up. Yeah. So the next step is, now that, did I actually say? Yeah, it's complete. Okay. So the next step is that we compile CMS with C++ modules. We have the same strategy as for root, so we want to compile CMS with modules with normal Clang. So the main reason for this is, again, if something breaks in Clang upstream, and we can take the nightly clang and compile CMS and it stops working, then we know someone broke Modis in upstream. And now we actually know that we have a bug in clang and we can fix it and can look at a commit log and see who broke it and why. So this is mostly a time saver for us. Also, we get root out of the equation, so if you have a bug, we know it's clang's fault and not like a root fault or anything else. So getting CMS to compile was more or less mostly just we fix includes, we add missing include, we fix includes, we add missing includes, we fix some typos in there. It was mostly not very breaking changes that changed a lot of things. We had to resolve a few cycles, I think just 2 in total. There are still some pull requests open, so 1 is still open. But yeah, the changes to CMS were not that dramatic. It's mostly just many small changes like fixed includes and this kind of stuff. What you also had to do is, the way modules work is that if you compile a module, it more or less follows all the textual headers, all the non-module headers it includes. So if you have a module that includes boost, it will actually kind of copy the headers from boost into the current module to make them available. So if you don't want to do this, and we actually have like multiple modules that have boost, for example, as a dependency, and we don't want to copy boost in every one of them, we have to say that boost is also a module, and then we make one boost module and we let the other people depend on this. So this brings down the sizes of the C++ modules. This also reduces, for example, things like runtime checks if the different boost copies in the modules are identical, and it also reduces the lookup time because we only have actually one boost in the lookup, which is from the boost module. So what we had to do is, we actually had to go with all the dependencies of CMS and also make C++ modules for them. So we went to things like boost, Gen4, HEPMC, PTR, and we have a very long list of other dependencies there that goes pretty much down to POSIX. We had to look at them, see what headers they're using, how they're structured, and then make C++ modules for them. So the end result is more or less that we have now many millions lines of code running with C++ code, mostly because CMS is quite big and we have more or less nearly everything from CMS compiling with modules, but also we have Boost and Gen4 and other libraries that are quite big, which are also in C++ modules now. So all of them are actually working with C++ modules with some minor patches that I have to upstream. But more or less this is the current state of CMS. So we actually can compile CMS, and we can also compile all the dependencies of CMS as C++ modules. So the status of this is also completed. And the final step would be we actually go to CMS and we actually say, now we actually start the dictionaries that we generate for CMS, that we also start producing C++ modules for CMS. And those C++ modules are the ones that we actually want to use during runtime. So we no longer parse CMS headers or boost headers or Gen4 headers, but instead what we're doing is we actually start loading the C++ modules from CMS. So what we more or less would do is we go to CMS and we try to go from bottom up and start turning normal modules and C++ modules and see if we hit any new bugs that we didn't catch before. And I hope the idea is that in the end we have a bunch of C++ modules for CMS. We attach them like during runtime. Root is then just using the C++ module instead of parsing the CMS headers. And yeah, that's more or less this. So there's one thing, just forgot this part. So there's one thing. What we need to do for C++ modules is we also need to get a system modularized, which means we need to make some configuration changes to the system. So one of the things we did for this is we have a script that actually takes your the setup you currently have and more or less adds all the changes it needs without actually touching the files. It just makes a Clang configuration file that you need during runtime. This is responsible for example, for finding out which boost version we have and then placing the right C++ module description there that actually root Clang or Clang can compile a C++ modules for boost. And the status here is not started. We more or less just finished the previous step and kind of still in the progress. There are pull requests open. So this is the overview of the work plan. We have the 6 steps. 5 of them are more or less done. And the final step is that we need to enable this for CMS runtime and see what's coming up there. And that's pretty much it from my side.
Okay, thank you, Raphael.
Thank you.
That's really making progress. Questions?
Well, I know it's early stages, right? Because the fixed point is still to be done. But do you have any early measurements on the actual impact that this does for runtime? Because the main goal, or like the stated goal at the beginning to switch to modules was interpreter is going to run faster, so root runtime is going to run faster, right? So do you already have any measurements on that?
The more or less the speed up we actually see here is, yeah, that's a good question. But depends how much work the code is actually doing in parsing. But what we have here, the speed up is more or less we run tutorials and measure them in runtime. So the thing is usually tutorials start up, they get the code, all the code they need. So you have a macro, you run it, it gets all the code it needs, client parses it, and then we more or less run. So the speed up time, the startup time is more or less what we get from the modules. The other thing is if you actually have during runtime, you get more and more code. But then you more or less see the same improvement to the time we spend on getting this code is more or less the time we see here. It's like around 25%.
Yeah, it's just that I don't have any idea in the experiments framework, like in CMS framework, what's the amount of interpreting that they do at runtime? I really don't know.
After startup, it's effectively 0.
Well, for I/O, you do calls to the interpreter.
Well, okay, unless root is doing something inside.
Yeah.
Okay, so it's whatever root does at I/O.
Yeah, but it depends how the experiments use it. So root does calls to the interpreter internally for quite a lot of stuff, but depends what you ask root to do, right?
So we're saving complex objects to root files.
So that, yeah,
right.
so essentially,
I think that's what everyone's doing, right?
Right?
Mostly, everyone I know about is doing that.
LHCb doesn't save complex objects.
Good.
It's simple objects. It depends.
Yeah. Anyway, yes, so that's being done. I don't know. It's not a big fraction of our CPU time, but although it's a place since it's not easily threaded that actually it helps a lot if that CPU time goes down. So time we're spending there.
Also another benefit is memory consumption. The big memory use. This is one of the major motivations where we introduced power declarations, because the peak memory just went up with root 6. And our power declaration brought it down a little bit. So because they introduced this lazy sort of evaluation approach where you only put in things only when you need them. And modules are going to one further than power declarations.
I guess that's what I didn't understand. But you're talking about RSS going up in the root examples.
Yeah.
Is that purely just at startup time, or?
Well, the thing is, the kernel can unload most of the stuff. The thing is why it's higher is, so we run it, and then the kernel loads the file. So we memory map it into our runtime memory, the modules file. But we actually don't read all the stuff there. The kernel just loads more or less all of it into it, and we get a lot of RSS.
It's really an RSS, though.
Yeah,
that's what we've just spent years getting grid sites to say is the right memory to look at.
It's not pages that we actually all use.
But it doesn't matter if it's still staying in RSS.
Well, the kernel is loading it in RSS because it's free. If it's not free, it's not loading it.
I don't understand what you mean. But it's something that stays in RSS, or it goes into just
the kernel can
where it doesn't get access.
But it's like the virtual memory. If you
I'm
don't.
just wondering what actually happens when you run a job. Do you see RSS staying high, or do you
if the memory is free, yes, because if the memory is free and the file is in memory, yes. If it's free if it makes sense for the kernel to preload it, then it makes sense that it actually goes in RSS. It's like a file you open, but the reason it shows up in RSS is because we memory map it. So it's like the cache that you usually have on Linux.
Okay, that's probably a bad thing if that's the way things behave for us.
Well, the reason why it gets to the RSS because RSS is more or less all your claimed memory. So if you actually would.
Right.
If you don't have a lot of memory,
we have a limited supply of RSS. That's the way to think about it, right?
If it's mem-mapped, it wouldn't go into RSS if we have limited supply.
Yeah, we're more or less asking the kernel. We're asking the kernel, we need a few bytes from this file, and we say it by memory mapping it. Right. And if the kernel says, I already have this file in memory, then it just assigns everything to our RSS.
So I'm lost about what you actually see. I'm not talking about theoretical statements. So in running a root tutorial, you see
you should see less RSS because the kernel is not loading it if it doesn't make sense for him to load it. But if you run it again, it maybe goes up because the file is already in memory. So the kernel kind of assigns, okay, this file is used by this guy, so you get all the memory there.
I think, for example, one thing that makes clear things is what happens when you memory map a 1 terabyte file. What is shown in your RSS? You don't have a terabyte of RAM, right?
Yeah, well, good question. What happens if you have such a big continuous memory?
Yeah. So if you answer that question, I think you understand if there is a problem. Because if you memory map a terabyte file and then your RSS is 1 terabyte, then it's really fake, right? But if it says, 1 gigabyte because you're using a huge cache, then you have to pay attention to it.
Actually, this reminds me that we actually tried that. And yes, it went to, well, it wasn't 1 terabyte, it was a huge amount as well. So we can redo the exercise and then come back and then discuss it. But something that we need to follow up.
Yeah, it's like opening a file. You just say open, and the kernel loads everything into memory at some point. Because you open it, you do nothing, and the kernel says, I'm doing anyway IO or something like this. It keeps it, but it's in the cache. So it's not shown in the RSS. You don't do anything to it, and then you close it, or you open the file again, and someone else read everything, and then, everything is anyway in the memory. You just don't get it to RSS, because if you say open and it's in a kernel cache, or if you say mmap, and it's also in a kernel cache, but it's counted to your RSS, then, yeah.
Okay. More questions? We're a little bit late. So if not, let's stop here and continue offline.